A blob of warm water the size of a continent is moving across the Pacific right now. Confirmed. It is rising from the deep ocean to the surface, and scientists say the heat volume matches the largest ever recorded. We are watching the early stages of what could become the most powerful El Niño in modern history. We will track this underwater heat pulse as it bends the jet stream, silences the Atlantic, burns the Amazon, and threatens food for billions of people. If you find this as alarming as we do, subscribe. You will want to follow this one. Brace yourselves. We begin. Off the coast of Peru, in the 1600s, fishermen noticed something wrong with the ocean. It happened every few years. Always around December, the water turned warm. The fish vanished. The birds disappeared from the sky. Nets came up empty for weeks. These were men whose families depended entirely on the sea. An empty net meant an empty table, so they paid attention to patterns the way a doctor watches a patient's pulse. And this pattern, this warm water arriving near Christmas, became something they talked about, warned each other about, and eventually named. They called it El Niño, Spanish for the little boy, a nod to the Christ child, since it arrived near the Christmas season. A warm, quiet visitor that seemed harmless at first. A few degrees of extra warmth in the water, some missing fish, nothing that looked like a global catastrophe. But those fishermen had no idea what they were actually naming. They could not see beneath the surface. They could not know that the warmth touching their boats was the top layer of something much larger. A system so enormous it could redirect rain away from entire continents. A force that could dry out rainforests the size of countries, flood deserts, and collapse food supplies for hundreds of millions of people. They just knew the fish were gone. For centuries, El Niño stayed a local mystery, a strange annual quirk along the South American coast. Fishermen passed the name down through generations. Scientists eventually heard it and started asking questions. Why did the water warm? Where was it coming from? Why did it disappear and then come back again years later? The answers took a long time, and the more scientists learned, the stranger it got. By the 20th century, researchers started connecting the dots. The warm water off Peru was linked to pressure changes across the Pacific. Those pressure changes were tied to wind patterns that stretched from South America all the way to Australia. One massive connected system spanning the entire width of the planet. What looked like a local fishing problem turned out to be one of Earth's most powerful climate engines. Scientists renamed the full system. The official term is the El Niño Southern Oscillation, a cycle of warming and cooling in the Pacific that shifts global weather on a scale that affects almost every country on Earth. But the original name stuck. El Niño, the one the fishermen gave it. There is something important in that. The first people to notice this force were ordinary men in small boats, watching the ocean for signs of trouble. They did not have satellites or computer models. They had experience and they had fear. And they were right to be afraid. The fish returned eventually. The warmth faded. Life went back to normal. And for a few more years, the ocean behaved itself. Then it happened again. This cycle, this swing between warmth and cold, has been repeating for longer than human history. Scientists have traced it back thousands of years through ice cores and ancient sediment. It has always come back. Right now, in 2026, something is building in that same Pacific Ocean. Something the satellites are tracking. Something that is already matching records. Something the fishermen could not have imagined when they named it with their empty nets on a quiet December morning. And what is building beneath the surface right now changes everything we thought we knew about the scale of this thing. Picture the Pacific Ocean as a bathtub. Now imagine someone tilting that bathtub slowly to one side. All the warm water slides to one end. The cold water rises on the other side. The whole thing is in balance, held there by one force, the wind. That is the basic setup of the Pacific, confirmed by decades of science. Trade winds blow westward across the equatorial Pacific. They push warm surface water away from South America toward Asia and Australia. This warm water piles up in the western Pacific, raising sea level there by about 2 feet higher than the eastern side. 2 feet across the same ocean, just from wind pushing water. On the South American side, where the warm water has been pushed away, something has to fill the gap. Cold water rises from the deep to replace it. This is called upwelling, and this cold water carries something critical: nutrients. Deep ocean water is rich with minerals and organic material. When it rises to the surface, it feeds tiny organisms called plankton. Plankton feed small fish. Small fish feed bigger fish. Bigger fish feed seabirds, dolphins, whales, and the fishing fleets that have worked these waters for centuries. The entire food chain along the South American Pacific coast runs on that cold upwelling, all of it powered by wind. This system has been running for so long and so reliably that ecosystems evolved around it. Animals migrated to it. Human communities built their economies on it. The wind created a food engine, and the food engine created a civilization along the coast. So here is the frightening part. The whole thing depends on the wind staying strong. If the trade winds weaken, even slightly, the warm water stops piling up in the west. It starts to spread back east. The cold upwelling slows. The nutrient supply drops, and a chain reaction begins that touches weather systems on every continent. Scientists measure wind strength across the Pacific constantly. They track ocean surface temperatures with satellites. They listen to pressure readings from buoys floating across thousands of miles of open water. The system they are watching is so large that no single measurement tells the whole story. You have to look at all of it at once to understand what is happening. And right now, what they are seeing is the winds beginning to ease. The warm water is no longer staying in the west, it is spreading. The upwelling along South America is already losing strength. The bathtub is starting to tilt back. This is how every El Niño begins: a weakening, a slide, a slow return of warmth to the eastern Pacific. It has happened before, dozens of times in the recorded record. Each time the world adjusts. Droughts appear in some places, floods in others. Seasons shift. Weather patterns break their usual routines. But here is something the current readings are showing that scientists did not expect at this scale. The warm water is not just spreading along the surface. Beneath the surface, in a layer scientists call the thermocline, something enormous has been building for months. A pulse of heat so large and so deep that the measurements are matching the biggest anomalies ever recorded in the historical data. That underground heat is rising, and when it reaches the surface, everything changes. What that pulse does next is something scientists have only seen hints of before, and the timing could not be more critical. It started with a number dropping, scientists monitoring the Pacific track, something called the Southern Oscillation Index, a measure of air pressure difference between the western and eastern Pacific. When it falls sharply, it means the atmospheric system holding the trade winds in place is losing grip. In early 2026, the index started sliding. The trade winds did not stop all at once. They never do. It is a gradual loosening, like a rubber band that has been stretched for months, slowly going slack. The winds ease, then ease more, and with each drop in wind speed, the warm water that had been pushed west stops in place. Then it starts to drift back east. This is the trigger. This is the moment every El Niño starts. A shift in atmospheric pressure, leading to a shift in wind, leading to a shift in ocean temperatures across the entire Pacific. And once it starts, stopping it is like trying to stop a wave with your hand. To understand the scale, picture the Pacific Ocean. It stretches 12,000 miles from coast to coast. It covers more surface area than all the land on Earth combined. The amount of water in it is so vast that if you melted every mountain on the planet and poured that water in, you would barely raise the level. This is the system that the trade winds were holding in balance. When those winds quit, that entire system starts to reorganize. The warm water begins sliding east. Sea surface temperatures in the central Pacific start rising. The atmosphere above them warms in response. That warmer air rises, altering pressure systems across the region. Those pressure changes affect wind patterns over Asia, Africa, and the Americas. One chain reaction, stretching across the whole planet, all triggered by a weakening of wind over open water. Scientists have a name for the rate at which this happens. They call it the coupling between ocean and atmosphere. When the two systems start feeding each other, the warming accelerates. Warmer water heats the air. Warmer air weakens the winds further. Weaker winds let the warm water spread more. And on it goes. In 2026, scientists watching the buoy network across the Pacific began seeing this coupling begin. The numbers were moving in the direction of El Niño emergence, quickly. Here is what makes this moment so unusual. El Niño events typically build slowly over many months. The signals are gradual, but the current readings are showing a pace and intensity that caught attention early. The subsurface ocean temperatures were already elevated before the atmospheric coupling began. The heat was already there, waiting. All it needed was the winds to ease. And the winds eased. What happens next depends on how fast the heat underground reaches the surface. Scientists are watching a massive pulse of warm water moving east beneath the ocean. A pulse so large, it has its own name in oceanography. A name that sounds technical, but describes something almost alive in the way it moves, carries energy, and changes everything it touches when it arrives. That pulse, and what it does when it breaks the surface, is the key to understanding why this event could be unlike anything recorded in the modern era. Right now, beneath the surface of the Pacific Ocean, something is moving. Scientists call it a Kelvin wave. It travels east along the equator, just below the surface, where the warm and cold layers of the ocean meet. It moves at about 3 to 5 miles per hour, which sounds slow, but the wave itself is enormous, hundreds of feet deep, thousands of miles wide, a wall of warm water pushing through the ocean like a slow-motion shockwave. You cannot see it from above. The surface of the ocean looks normal, but instruments deep in the water, attached to buoys anchored across the Pacific, are tracking its movement in real time. This is the underground highway of El Niño, and what is traveling on it right now is heat. Kelvin waves form in the western Pacific when wind patterns shift. As trade winds weaken, they create a disturbance in the ocean. That disturbance travels east as a wave of warm water pressed down into the thermocline, the boundary layer between warm surface water and the cold deep. As the wave moves east, it pushes the thermocline downward, trapping warm water beneath it. When the wave finally reaches the eastern Pacific, near South America, it rises. The warm water it has been carrying for weeks surfaces. And that is when sea surface temperatures spike and El Niño conditions take hold at the surface. In early 2026, satellites and deep ocean buoys confirmed the presence of an active and significant Kelvin wave moving east. Here is why this one drew immediate attention from scientists. The volume of warm water in this wave is matching the largest subsurface anomalies ever recorded in the historical dataset. That means the amount of heat currently traveling beneath the ocean is equal to the biggest readings scientists have seen since they started keeping careful records. The wave is deep, wide, and powerful. To put it in terms that are easier to picture, imagine filling every swimming pool in the United States with hot water and then somehow moving all of that heat through the ocean as a single invisible pulse. The actual volume of displaced warm water in this wave dwarfs even that image. The Pacific is enormous, and this wave is significant even by Pacific standards. Scientists track Kelvin waves using a network of buoys called the Tropical Atmosphere-Ocean Array. These buoys float at fixed locations across the equatorial Pacific and measure temperature at multiple depths. The data they transmit allows scientists to see the wave's position, speed, and temperature signature as it moves. As of May 2026, that data showed the wave arriving in the central and eastern Pacific, with the warmest subsurface readings concentrated just below the surface, and rising. Rising is the critical word. When the thermocline lifts and the warm water below it reaches the surface, the effect on the atmosphere above is immediate and dramatic. Sea surface temperatures jump, air pressure shifts, the atmospheric coupling that drives the full El Niño system locks in and accelerates. The wave has been traveling for months. It is nearly there. And when subsurface heat of this volume reaches the surface all at once, the question scientists are now asking is not whether El Niño will happen. The question is how extreme it will get. Scientists do not alarm easily. They are trained to wait for data, to check models against observations, to stay cautious when public attention is high and pressure to make a bold statement is intense. They have seen false alarms before. They have watched conditions that looked threatening fade into nothing by summer. So when the scientists monitoring the Pacific in 2026 started using words like record and unprecedented to describe what they were seeing, that meant something. The measurement drawing the most attention is the volume of subsurface warm water anomalies in the Pacific. An anomaly in this context means a temperature reading higher than the historical average for that location, depth, and time of year. Scientists calculate the average from decades of measurements and then compare what they are seeing right now to that baseline. The difference is the anomaly. In May 2026, those anomalies in the subsurface Pacific matched the largest values in the recorded dataset. The historical record for these measurements stretches back to the 1970s, when the buoy network became reliable enough to trust. Over roughly 50 years of careful observation, these readings are the biggest ever seen. To understand why that matters, think of the subsurface ocean as a storage tank. Heat builds up in it over months, driven by atmospheric conditions. When El Niño arrives and that heat surfaces, it determines the event's intensity. A bigger tank means a bigger spike. A bigger spike means more heat released into the atmosphere. More heat in the atmosphere means stronger disruption to weather systems around the world. The current tank is full. Compare that to the 1997 to 1998 El Niño, the strongest ever recorded in modern history. That event caused massive crop failures across Asia, catastrophic flooding in South America, severe drought in Australia, and wildfires in Indonesia that burned for months. Scientists measured sea surface temperature anomalies of around 4 to 5 degrees Fahrenheit above normal at its peak. Global temperatures that year spiked to levels that set records at the time. The current subsurface readings are comparable to what preceded that event. Some seasonal models are projecting that sea surface temperatures could spike by up to 5.5 degrees Fahrenheit above normal during this event. That would match or exceed the 1997 peak. Scientists are careful to say that models in spring have higher uncertainty than models in late summer, so the final strength is not locked in. But the building blocks visible right now are the largest on record. There is one additional factor that sets this event apart from all previous ones. The ocean is warmer than it was in 1997. The atmosphere is warmer. The baseline temperature of the planet has risen because of decades of human-caused warming. When a natural heating cycle layers on top of a warmer planet, the combined effect is amplified. Scientists call this the climate change multiplier. The natural event stays the same size, but the world it hits is already running hotter. The fishermen who named this thing in the 1600s had no idea. The scientists who first mapped it in the 20th century could not have predicted this version of it. And the version building right now may exceed anything the modern world has been designed to handle. And what happened when officials finally looked at all of this data together is the part that triggered official warnings. On May 14, 2026, the National Oceanic and Atmospheric Administration issued an official El Niño Watch. A watch is a formal declaration. It means scientists have reviewed the available data across ocean temperatures, atmospheric pressure, wind patterns, and subsurface heat, and concluded that conditions favorable for El Niño development are present and likely to continue. This was not a quiet announcement buried in a technical bulletin. The agency released its full diagnostic discussion, laying out the probabilities in stark terms. An 82% chance of El Niño emerging between May and July of 2026, a 96% chance that the pattern continues through the winter of 2026 to 2027. Those numbers reflect how far along the development already is. A 96% probability of continuation through winter means scientists are essentially certain the event will be active for the next 8 months, at minimum. The uncertainty is no longer about whether it happens. The uncertainty is about how strong it gets. To issue a watch, the agency relies on a consensus of global climate models. These models ingest data from satellites, ocean buoys, weather stations, and atmospheric sensors around the world. They run simulations of how the atmosphere and ocean will interact over the coming months. Each model produces a slightly different forecast. Scientists look at the spread of those forecasts, identify where models agree, and weigh confidence accordingly. The current level of model agreement on El Niño emergence is high. Sea surface temperatures in the east-central equatorial Pacific already measured 0.72 degrees Fahrenheit above the long-term average in May 2026. That number seems small. But in ocean terms, where temperatures change slowly and every fraction of a degree carries enormous energy, 0.72 degrees represents a significant and measurable shift. It is early, the full warming has not arrived yet. The subsurface heat is still moving upward. What the watch signals to governments, agricultural planners, disaster response teams, and public health officials is that preparation time is limited. El Niño events do not announce themselves with weeks of warning at their peak. The warning window exists now, in the months before conditions lock in. Countries that prepare during the watch phase, stockpiling food reserves, pre-positioning emergency supplies, updating flood and drought contingency plans, are the ones that come through the event with less damage. Countries that wait until conditions are obvious typically find themselves responding to a crisis that is already larger than their capacity to manage. The National Oceanic and Atmospheric Administration's watch is that early signal, an official instruction to start preparing. And yet, even with those preparations, the scope of what this event could affect is so large that no single country can manage it alone. The physical changes already underway in the Pacific are beginning to reach the surface. When they do, the first places to feel it will be the places least able to prepare. And one of the most devastating effects of what is coming has nothing to do with storms or floods. It starts with fish disappearing from the water. Every year, spring creates a problem for climate scientists. There is a gap in forecasting skill during spring that meteorologists have studied for decades. They call it the spring predictability barrier, and it sits directly in the path of this developing El Niño. Here is why it exists. El Niño forecasts depend on understanding how the atmosphere and ocean are coupled together. Are they feeding each other? Is the warm water driving atmospheric changes that in turn amplify the warming? When that coupling is strong and locked in, models can project months ahead with reasonable confidence. During spring, that coupling weakens. The atmosphere over the Pacific becomes less organized. Wind patterns are more variable. The connection between ocean temperatures and atmospheric response becomes harder to read. Models that were tracking well in winter can drift apart during spring, producing a wider range of possible outcomes. This creates a forecasting blind spot. Scientists know something large is building. The subsurface data is clear, the wind trends are real, but the exact peak strength of the event, the number that determines whether it becomes a moderate event or a historic super event, passes through this uncertain window before models can nail it down. The 82% probability figure from the National Oceanic and Atmospheric Administration reflects this limitation. It expresses high confidence in El Niño emerging, but the strength projection carries more uncertainty than it will in August or September, when the spring barrier has passed and models can see the full picture. This matters for a specific reason. The difference between a moderate El Niño and a super event is enormous in terms of real-world damage. A moderate event shifts rainfall patterns and disrupts some agricultural regions. A super event can trigger simultaneous droughts on multiple continents, collapse fisheries, fuel massive wildfires, and push global temperatures to record highs. The window between those two outcomes is still open. Think of it like watching a hurricane form in the ocean. You can see it spinning. You can see it gaining energy. You know it is heading toward land, but the exact track, the exact landfall location, the exact peak wind speed, those answers come closer to arrival, not in the early days of formation. Forecasters issue watches and warnings based on what they can confirm, while being honest about what they cannot yet know. Climate scientists are in that same position right now. They can see the heat building beneath the Pacific. They can confirm the winds are easing. They can calculate the probabilities, but the final strength of this event will only become clear once the spring barrier has passed and the atmosphere locks back into the ocean signal. That clarity is coming in the next few months, and the fact that scientists are already alarmed, before the spring barrier has cleared and before models have produced their most confident forecasts, says something important about how unusual the current readings are. Because even inside this window of uncertainty, one physical process is already confirmed and already underway, and it moves on its own schedule, with no regard for what the models say. The heat pulse beneath the Pacific is still rising toward the surface, and what happens the moment that heat arrives changes everything visible above the water. Imagine a mass of warm water the size of the continental United States sliding across the Pacific Ocean. That is what satellites are tracking right now. A physical body of warm water, confirmed by surface measurements and orbital instruments, moving eastward across the equatorial Pacific towards South America. This is one of the most striking visual realities of El Niño and one of the hardest to picture from shore. The ocean surface looks the same to the naked eye. Blue water, waves, horizon. But temperature sensors reveal something moving beneath that surface, something massive and slow and carrying an almost unimaginable amount of energy. Sea surface temperature maps, the kind produced daily by satellites measuring the heat radiating off the ocean, show the warm pool as a bright orange and red region spreading east across the equatorial Pacific. The colors represent temperatures significantly above the historical average. Scientists watch these maps the way a doctor watches a scan, looking for how the bright region is growing, which direction it is moving, and how intense the core is becoming. In May 2026, that warm region was already measurable and expanding. The central and eastern equatorial Pacific showed surface temperatures running above average and climbing. The movement of this pool matters because of what it does to the atmosphere directly above it. Warm ocean water evaporates faster. More evaporation means more moisture in the air. More moisture in the air changes where and how rain forms. When the warm pool was confined to the western Pacific near Australia and Asia, those regions received the moisture. When the pool moves east, it drags the moisture with it. The rain follows the heat. Regions that typically sit beneath the warm pool get drenched. Regions that lose the warm water above them see their rain disappear. A continent that has relied on regular monsoon rainfall for centuries can watch that rainfall system shut down in a single season because the heat source feeding it has shifted several thousand miles to the east. This is confirmed climate physics. Ocean temperature controls atmospheric moisture. Atmospheric moisture controls rainfall. Rainfall controls whether crops grow, rivers run, and reservoirs stay full. And the pool is still moving. One additional physical effect of this warm pool is confirmed and often overlooked. It actually raises sea level. Warm water expands. As the warm pool moves east and spreads, the sea surface physically rises along the western coast of South America. Satellite measurements have confirmed temporary sea level increases of several inches along these coasts during major events. Several inches sounds minor. Combined with storm surge, high tides, and waves, several inches can push coastal flooding into areas that were previously protected. For low-lying coastal communities with no seawalls and limited resources, that addition is the difference between wet streets and submerged homes. The pool is still growing, still moving east, still drawing heat from below as the Kelvin wave beneath it continues to rise. And when it reaches full strength along the South American coast, the cold upwelling that has fed those waters for centuries will face something it has never been designed to handle. Most people have heard of the jet stream. Very few have a clear picture of what it is or why it matters so much. Here is the simple version. The jet stream is a river of fast-moving air high in the atmosphere. It flows from west to east around the planet at an altitude of roughly 6 to 9 miles above the surface, where commercial planes cruise. It travels at speeds between 60 and 200 miles per hour, making it one of the most powerful continuous wind currents on Earth. It exists because of temperature differences. Warm air and cold air meet in a band across the northern hemisphere, and where they meet, pressure differences create a concentrated river of high-speed wind. The jet stream follows that boundary. When the boundary shifts, the jet stream shifts with it. Normally, the jet stream follows a relatively predictable path, arcing across the North Pacific and North America, then continuing over the Atlantic. Weather systems, meaning the storms, rain bands, and pressure zones that determine what you see outside your window, travel along the jet stream like boats on a river. The river's path determines where those storms go. Now here is where El Niño enters. When the tropical Pacific warms significantly, it changes the temperature pattern across the region. That change reshapes where warm and cold air masses meet, and that shift physically moves the jet stream off its usual path. A relocated jet stream relocates everything traveling along it. Storms that would normally track across the northern United States shift southward. Rain systems that would hit the Pacific Northwest instead sweep through California. Winter storms that might have stayed mild in the south can intensify. The entire weather delivery system for North America reroutes. And this is true across multiple continents simultaneously. The jet stream over the Pacific affects weather patterns over North America. A separate atmospheric river system influences rainfall in South America. Pressure changes over the tropical Pacific ripple through the Indian Ocean system, affecting the monsoons that water crops across India, Southeast Asia, and East Africa. One warmer ocean, multiple rerouted weather systems, on multiple continents, at the same time. To put the scale in physical terms, the jet stream carries more air volume than all the rivers on Earth carry water. It is the dominant force shaping day-to-day weather across the northern hemisphere. Shifting it even slightly south changes precipitation patterns across millions of square miles. Scientists have mapped how the jet stream responds to different El Niño intensities by studying past events. A moderate warming nudges it. A super event can lock it into a dramatically different position for an entire season, fundamentally rewriting the weather calendar for hundreds of millions of people. The current developing event has the heat content to potentially force one of those larger shifts. The jet stream is already beginning to respond, and the effects of that response are already showing up on the ground in ways that forecasters are watching very carefully. Because what a rerouted jet stream produces on the surface is not subtle. And what it does too, when the jet stream shifts, the first thing that changes is rain, specifically who gets it and who does not. During a significant El Niño, the southern tier of the United States tends to receive more rainfall than average through winter and spring. California, the Gulf Coast, and the Southeast can see repeated storms where they might normally have mild, dry winters. At the same time, the Pacific Northwest and parts of the northern United States tend to go dry. The storm track that would typically carry moisture inland across Oregon and Washington gets pushed south. Snow that would have fallen in the mountains that feed rivers and reservoirs across the west instead falls somewhere else, or does not fall at all. This is a direct consequence of the jet stream shift. The storms do not disappear, they reroute. For farmers, this timing matters enormously. Winter snowpack in the Sierra Nevada and the Rocky Mountains is what fills reservoirs through the dry summer months. If a shifted jet stream delivers rain to the coast but skips the mountains during a warm, snowless winter, the spring melt never comes. Rivers run low. Reservoirs drop. Water rationing begins by June in places that depend on that snowmelt. Meanwhile, the Gulf Coast gets soaked. Rivers in the south run high. Roads flood. Crops planted in fields that are too wet rot before they can be harvested. One El Niño, two opposite problems, happening at the same time a few hundred miles apart. Globally, the effect is even more dramatic. In Australia, El Niño events are strongly associated with drought. The eastern side of the continent, which depends on rainfall from the Pacific, sees its moisture supply cut off as the warm pool moves east and the rain follows it. Reservoirs dry up, farms fail, wildfires ignite across dried grasslands and bush. In East Africa, specifically countries like Kenya, Ethiopia and Somalia, El Niño can bring either devastating floods or severe drought, depending on the season and the specific configuration of the warming. Communities that depend on seasonal rains for subsistence farming face total crop failure in the worst years. In South and Southeast Asia, where the monsoon feeds over 1 billion people, El Niño disrupts the monsoon's timing and strength. A late or weak monsoon means drought in the planting season. A shifted monsoon means flooding in areas that were not prepared. All of this rerouting in Australia, Africa, Asia, and North America traces back to one ocean warming. One shift in sea surface temperature changing atmospheric pressure, which shifts the wind, which shifts the jet stream, which shifts the storms, which shifts the rain. The scale of that chain reaction, one ocean affecting every continent simultaneously, is confirmed climate science, and one of the most powerful examples of how connected Earth systems really are. And the communities most damaged by the rerouting are the ones with the least ability to recover, the ones that had already been pushed to the edge by previous droughts, previous floods, previous years of climate stress. But drought and flood are only part of the picture, because the same warming ocean that reroutes the rain is doing something else entirely to the water beneath it, something that started the moment cold water stopped rising along the South American coast. Here is something most people never expect. El Niño raises the sea level. Temporarily, in specific places, but physically, measurably and confirmed by satellite. The mechanism is straightforward once you understand the ocean basics. Water expands when it warms. Cold water is denser and sits lower. Warm water is less dense and sits slightly higher. During normal Pacific conditions, the Western Pacific near Australia and the Philippines has higher sea levels than the Eastern Pacific near South America, because that is where the warm water has been pushed by the trade winds. The difference is roughly 2 feet across the entire ocean. When El Niño arrives and warm water surges east, that heat fills the Eastern Pacific. The water there expands. Sea levels along the western coasts of the Americas rise, not by 2 feet, but by several inches in places, and sometimes approaching a foot during very strong events. That sounds small. Coastal areas sit at specific elevations. A road that sits 8 inches above the normal high tide line gets flooded when the base sea level rises 8 inches, and a storm adds another foot of surge on top. Neighborhoods built at one level of risk suddenly face a higher level, with no structural changes to protect them. During the 1997 to 1998 El Niño, the sea level rise along the California coast contributed significantly to winter storm damage. Coastal erosion accelerated. Cliffs that had held for decades collapsed into the ocean. Beach communities flooded during storms that would have been manageable under normal sea level conditions. Scientists use radar altimeters on satellites to measure sea level variations across the ocean with centimeter-level precision. These instruments measure the actual height of the ocean's surface from orbit and have been tracking Pacific conditions continuously for decades. In the current event, satellite readings already confirm a measurable rise in sea surface height across the central and eastern equatorial Pacific as the warm water pool expands. The rise will intensify as the event peaks. For coastal cities built close to sea level, this temporary rise lands on top of a permanent problem. Global sea levels are already higher than they were 50 years ago because of long-term warming. The permanent rise and the temporary El Niño rise stack. Communities that were managing one problem now face both at once. Add storm surge from the more intense storms that a warmer ocean generates, and the result is flooding that exceeds any historical baseline those communities were built to handle. The western coasts of South America and Central America feel this most directly. Communities in Peru and Ecuador have watched El Niño reshape their coastlines within living memory. In 1997, entire towns flooded, roads washed out. The physical geography of some coastal areas changed permanently from a single event. The current warm pool is still expanding. The sea level along these coasts is still rising, and the fish are already gone. The Peruvian fishermen who named El Niño in the 1600s were not wrong about the danger, they just did not know how far it reached. The immediate and confirmed effect of El Niño on ocean ecosystems starts with cold water, specifically with the loss of it. Under normal Pacific conditions, cold water rises along the South American coast in a process called upwelling. This cold water comes from deep in the ocean and carries nutrients, nitrogen, phosphorus, iron. These nutrients fertilize the surface layer of the ocean and feed the microscopic organisms at the base of the food chain. Plankton bloom in these waters. Anchovies and sardines swarm to eat the plankton. Larger fish follow. Seabirds nest in massive colonies on the coastal cliffs because the fish are always there. When El Niño arrives and warm water surges east, it sits on top of the cold water like a lid. The upwelling slows or stops entirely. The nutrients stay trapped deep below. The plankton disappear from the surface. Within weeks, the fish follow them down or scatter to colder regions. The anchovies vanish. The seabirds that depend on them starve and abandon their nesting grounds. This is not a small disruption. Peru's anchovy fishery is one of the largest in the world and a major source of fish meal that feeds poultry and livestock across multiple continents. When El Niño collapses the anchovy population off Peru, that disruption travels through global food supply chains within months. During the 1997 to 1998 event, the anchovy catch off Peru dropped by more than 80%. Fishing communities that had operated for generations lost their income. Processing plants closed. Sea lion populations, which feed heavily on anchovies, crashed. Thousands of sea lion pups died on beaches because their mothers could not find enough food. That die-off was visible. Tourists photographed emaciated sea lions lying on beaches in the Galapagos Islands. Seabird colonies that numbered in the tens of thousands fell silent. The coastal ecosystem, which had evolved around a reliable food chain for thousands of years, collapsed in a matter of weeks. The speed is the part that is hard to accept. Weeks. The entire food web, from plankton to apex predators, restructures in weeks because the cold water stopped rising. In 2026, scientists are already observing early signs of reduced upwelling along the South American coast. Sea surface temperatures in the region are rising. The nutrient-rich cold water is retreating. The collapse has not reached full intensity yet. The warm pool is still expanding. The thermocline has not fully suppressed the upwelling along its entire range. But the fish already know something is wrong. They are following the cold water as it retreats. The fishing villages are getting quieter, and farther out in the ocean, In the shallow, warm water reefs that ring tropical coastlines across the Pacific and Indian Oceans, another kind of collapse is already beginning, one that is silent, slow, and almost impossible to reverse once it starts. A coral reef looks alive. The bright colors, the intricate structures, the endless variety of fish weaving through it. All of it traces back to a relationship between coral animals and tiny algae called zooxanthellae that live inside their tissue. The algae give the coral its color. The algae also produce food through photosynthesis, supplying the coral with up to 90% of its energy. In return, the coral gives the algae a protected place to live. This partnership has existed for hundreds of millions of years. Coral reefs have survived ice ages, meteor impacts, and mass extinctions. They have shown a resilience that seems almost impossible, and the limit is temperature. When water temperature rises even 2 degrees Fahrenheit above the summer maximum that a coral is adapted to, the relationship breaks down. The coral becomes stressed. It expels the algae from its tissue. Without the algae, the coral loses its color and turns stark white. Scientists call this bleaching. Bleached coral is alive but starving. If temperatures drop quickly, the algae can return and the coral recovers. If temperatures stay elevated for weeks, the coral dies. A dead reef does not recover on human timescales. It can take decades for new coral growth to establish where a thriving reef once stood, and only if conditions allow, El Niño events have caused some of the largest coral bleaching events in recorded history. The 1997 to 1998 event triggered the first globally synchronized mass bleaching ever documented, killing coral across the Pacific, Indian, and Caribbean reefs simultaneously. Scientists have never seen anything on that scale before. The 2016 event caused the worst bleaching ever recorded on Australia's Great Barrier Reef, killing roughly 30% of the reef in a single year. The reef is the size of Italy. 30% of it died in 1 year. In 2026, sea surface temperatures across the tropical Pacific are already elevated. The Indo-Pacific region, which hosts some of the highest coral diversity on Earth, is showing early warming signals consistent with bleaching risk. Coral bleaching is especially damaging because reefs function as nurseries for the ocean. A quarter of all marine species spend part of their life cycle in a reef. Fish that grow up in reefs scatter into the open ocean and form the basis of fisheries that feed hundreds of millions of people. Healthy reefs also protect coastlines. They absorb wave energy and reduce storm surge damage. When a reef dies, the coastline behind it faces stronger wave impact with every storm. The current warming trajectory puts reef systems across the Pacific and Indian Oceans in a high-risk window. The ocean temperatures needed to trigger bleaching are within reach of where current forecasts are pointing, and the bleaching, when it comes, will happen quietly, underwater, out of sight. But in the Atlantic Ocean, something else is happening that is anything but quiet. The same Pacific warming that is threatening the reefs is simultaneously doing something dramatic to the storm season, shutting down one ocean's hurricanes while charging up another's. Hurricane forecasters in the United States watch the Pacific with unusual attention. The reason is counterintuitive. A warming Pacific Ocean can reduce Atlantic hurricane activity. This is one of the better understood remote effects of El Niño, confirmed across multiple event cycles. Here is the mechanism. Atlantic hurricanes need specific conditions to form and grow. They require warm sea surface temperatures, low wind shear, and a moist atmosphere. Wind shear is the change in wind speed or direction between different altitudes. When wind shear is high, it tears apart the organized rotation of a developing storm before it can build into a hurricane. During El Niño, the altered jet stream and atmospheric changes over the tropical Pacific create stronger upper-level winds over the Atlantic. Those winds increase vertical wind shear across the main hurricane development region of the Atlantic, roughly between the African coast and the Caribbean. Developing storms get torn apart before they can strengthen. Fewer hurricanes form. The ones that do form struggled to intensify. The 1997 to 1998 El Niño coincided with one of the quietest Atlantic hurricane seasons on record. Only 3 hurricanes formed that year, well below the historical average of around 6. This is confirmed El Niño physics, and on the surface it sounds like good news. But there is another side to this. While the Atlantic goes quiet, the Pacific gets more active. El Niño's warm water provides more fuel for Pacific typhoons. The storms that strike the Philippines, Japan, Vietnam, and other Western Pacific nations grow stronger and arrive more frequently. Communities that were already hit hard by the previous season face a more intense one, and the Atlantic suppression is not guaranteed protection. A reduced number of storms does not mean zero storms. Some of the most destructive Atlantic hurricanes in history have formed during El Niño years. They were fewer in number, but some reached extreme intensity. A quieter season with one catastrophic storm causes more damage than an average season with 6 moderate ones. Forecasters in 2026 are watching this balance carefully. El Niño suppression of Atlantic hurricane activity is expected to continue into the peak Atlantic hurricane season of late 2026. That may reduce the total number of storms, but the storms that do form will develop in an atmosphere that is warmer and more moisture-laden than any previous El Niño season on record due to the climate change baseline. The math on what that combination produces for storm intensity is not settled. What is settled is what El Niño is doing on land, far from any ocean. The same atmospheric changes that suppress Atlantic storms are altering rainfall patterns over the world's largest forests. And in those forests, the effect of reduced rainfall is not measured in missing storms. It is measured in fire. The Amazon should not burn. A tropical rainforest is one of the wettest places on Earth. The trees release so much moisture through their leaves that they create their own rainfall. The soil stays saturated. The air is thick with humidity. Under normal conditions, starting a fire in the Amazon is extremely difficult. El Niño removes those conditions. When El Niño shifts rainfall patterns over South America, the Amazon experiences drought. The rains that normally arrive on schedule, feeding the rivers and keeping the forest floor wet, arrive late, arrive weakened, or skip entire regions entirely. The soil dries, the leaf litter dries, the trees already stressed by the heat drop leaves that dry on the ground. Farmers and ranchers in the Amazon use fire to clear land. They have done this for generations. Under normal wet conditions, these fires are mostly controllable. They burn the cleared area and stop at the edge of the forest because the living forest is too moist to catch. During El Niño drought, the forest is no longer moist. The fires spread. They jump from cleared land into the standing forest. They move along the dry leaf litter on the forest floor, moving into areas that have never burned in recorded history. The 1997 to 1998 El Niño produced some of the worst fires in Amazon history at that point. Millions of acres burned across Brazil. Fires in Indonesian Borneo and Sumatra, which depends on the same monsoon rainfall system that El Niño disrupts, burned so intensely that the smoke covered an area the size of the continental United States. Airports closed. Air quality in regional cities reached hazardous levels. Thousands of people were hospitalized with respiratory illness. The Amazon's role in global climate goes beyond its size. The forest holds more carbon in its trees and soil than a decade of global human emissions. When it burns, that carbon releases. A large enough fire event in the Amazon can meaningfully accelerate the same warming that is making El Niño more severe. Scientists call this a feedback loop. El Niño dries the forest. The dried forest burns. The burning releases carbon. The released carbon warms the planet. A warmer planet intensifies the next El Niño. In 2026, drought conditions linked to the developing El Niño are already being forecast for parts of the Amazon basin and the Indonesian archipelago. Fire weather conditions are expected to be elevated across both regions during the event's peak period. The scale of potential fire damage during a super event in a forest already stressed by years of drought and deforestation is something that scientists describe carefully, with emphasis on the word irreversible. Once old-growth forest burns, it does not come back as old-growth forest. What grows in its place holds a fraction of the carbon, supports a fraction of the species, and produces a fraction of the rainfall of the original. The loss is permanent on any timescale that matters to humans. But while the forests burn, something else entirely happens on the opposite end of the moisture spectrum. In the driest places on Earth, El Niño does the last thing anyone expects. In the driest desert in the world, it rained. The Atacama Desert in Chile holds the record for the lowest average rainfall of any place on Earth. Parts of it receive less than 1/10 of an inch of rain per year. Some weather stations in the Atacama have gone multiple decades without recording a single measurable rainstorm. The landscape looks like Mars: red rock, cracked clay, no vegetation. During El Niño events, that changes. The same atmospheric shifts that send drought into the Amazon can funnel unusual rainfall into the Atacama and other desert regions along the South American coast. When the rain arrives, something extraordinary happens. Seeds that have been dormant in the soil for years, some for decades, respond. The Atacama blooms. Millions of flowers cover hillsides that were bare rock weeks before. Yellow, purple, pink, and white blooms spread across valleys that have not seen color in years. This event is rare enough that it has its own name in Spanish: Desierto Florido, the flowering desert. Scientists studying the Atacama bloom have found seeds that can remain viable in dry soil for over 20 years, waiting for exactly this kind of rainfall event. The plants that grow from them complete their entire life cycle, germinating, flowering, and producing new seeds within weeks. Then, the desert goes back to sleep. The same effect appears in other arid regions around the world during El Niño events. Parts of the Mojave Desert in California and Nevada, normally dry through winter, can receive several times their average annual rainfall during a strong El Niño. Normally dry riverbeds fill, flash floods surge through arroyos that have been empty for years. Wildflowers carpet hillsides across the Sonoran Desert. This is real and confirmed science, not a rare coincidence. El Niño's shifted rainfall patterns specifically direct moisture into regions that are climatologically starved of it, while pulling rain away from regions that depend on it. The winners and losers are almost perfectly reversed from normal conditions. The problem is that the communities built in desert regions are built for desert conditions. They are engineered for drought, for dry riverbeds, for rare rainfall. When El Niño delivers months of rain instead of weeks, the infrastructure fails. Flash floods destroy roads, bridges collapse over rivers that are supposed to be dry. Homes built in floodplains that have been safe for generations suddenly sit underwater. Peru, in particular, has experienced catastrophic flooding along its normally arid northern coast during strong El Niño events. The 1997 to 1998 event caused floods that killed hundreds of people and destroyed infrastructure that took years to rebuild. Beautiful and catastrophic at the same time. The same event that blooms a desert drowns a town. And while some regions receive too much water, others begin losing something far more critical. Something that billions of people depend on every day, that no amount of emergency response can replace once it is gone. Food does not grow on its own schedule, on temperature windows, on seasons that farmers have tracked for generations, planting within specific weeks, irrigating to specific amounts, harvesting before the window closes. The entire global food system is built around the assumption that the climate will behave more or less as it did the year before. El Niño removes that assumption. When rainfall patterns shift across multiple continents simultaneously, planting seasons break down. Fields that should be wet stay dry. Fields that should be dry flood. Crops planted in the wrong conditions either fail to germinate, drown in saturated soil, or wither before harvest. The 1997 to 1998 event demonstrated this at scale. Indonesia lost rice harvests across large parts of the country. The Philippines saw widespread crop failure. India's monsoon arrived weakened and late, hitting the planting window at the worst possible time. Southern Africa experienced severe drought, with Zimbabwe, Zambia, and Mozambique all reporting major food shortages. These were not isolated events. They happened at the same time because they shared the same cause: one warmer ocean reshaping the rain across every continent. The compounding effect is what turns a bad harvest into a crisis. When one country fails, it buys from others. Global food markets adjust. Prices rise. Poorer countries pay more. When multiple countries fail simultaneously, there is nothing left to buy at any price. A spike in ocean temperature in the Pacific of just a few degrees can trigger crop shortfalls across Asia, Africa, and the Americas at the same time. Global food prices respond within months. Families in countries that did not experience any extreme weather still pay higher prices for rice, wheat, and corn because the farmers who grew those crops are on the other side of the world, staring at a field that received no rain. Maize production in southern Africa is particularly vulnerable. This is a region where millions of families grow their own food on small plots of land, with no irrigation, no crop insurance, and no savings to survive a failed season. One bad year can mean hunger. 2 consecutive bad years, which El Niño followed by La Niña, can push entire communities into severe food insecurity. In 2026, forecasters are already flagging agricultural risk zones across Southeast Asia, Eastern Africa, and parts of South America based on the developing El Niño pattern. Governments and international aid organizations are beginning to assess stockpiles and pre-position food assistance. The warning is out, the window to prepare is still open. But even with preparation, the mathematics of a global food system hit by simultaneous regional failures are deeply uncomfortable. Global grain reserves, the emergency buffer that exists to absorb regional shocks, have been lower in recent years than historical safety thresholds recommend. A super event landing on a system with limited reserves and multiple vulnerable regions at once creates a risk profile that food security analysts describe with unusual urgency. And the pressure on food is only one dimension of what this event is building toward, because simultaneously, something else is happening to the planet's baseline temperature that is going to make every other effect significantly worse than the historical record would suggest. The Pacific has warmed before. El Niño is ancient. Scientists have traced its fingerprints in ice cores drilled from Andean glaciers, in ancient lake sediments in the Andes, in coral skeletons that recorded ocean temperatures centuries before any thermometer existed. The cycle has been running for thousands of years. It has always disrupted weather. It has always caused damage. But every previous El Niño happened in a colder world than this one. The global average surface temperature today is roughly 2 degrees Fahrenheit higher than it was in the mid-1800s, before large-scale industrial emissions began warming the atmosphere. That 2-degree shift is the accumulated result of over 150 years of burning coal, oil, and natural gas. The heat did not disappear, it stayed in the atmosphere and the ocean. Think of it this way. Imagine you are baking something in an oven that normally runs at 350 degrees. Now imagine someone secretly turned the dial up to 365 degrees and left it there. Everything you bake now comes out hotter than expected. The recipes still work the same way. The chemistry is the same. But the results are consistently more extreme because the starting temperature is higher. El Niño is the same recipe it has always been. The oven is hotter. This matters because El Niño's damage is tied to temperature anomalies, the difference between normal and what actually happens. When the baseline rises, the anomaly builds on top of a higher starting point. A 3-degree spike on top of an already elevated ocean temperature produces more atmospheric energy than the same 3-degree spike would have produced 50 years ago. More energy means stronger storms, more intense droughts, heavier rainfall events, and higher peak temperatures during the event. Scientists call this the climate change multiplier. The natural cycle amplifies when layered on a warmer baseline. The specific projection drawing attention right now is for the year 2027. Multiple climate research teams have flagged this year as a candidate for the warmest ever recorded on Earth, combining the lingering heat of the El Niño peak with the elevated planetary baseline. The previous record was set in 2023 and then again in 2024. The warming trend is accelerating. What makes this projection alarming is that heat records have consequences beyond the numbers on a graph. Each new record pushes ecosystems, agriculture, and infrastructure closer to thresholds they were never designed to handle. Coral reefs have temperature limits. Crops have temperature limits. Human bodies have temperature limits. And some of the most vulnerable populations on Earth already live in climates running close to those limits during normal years. A record-breaking year, powered by El Niño amplified by climate change, tests all of those limits at once. The natural and the human-caused are no longer separate. They are locked together now, feeding the same event. And the event that emerges from that combination is something no historical record fully prepares us for, because the heat that is coming has already been compared to something specific, something that happened once before and left a mark on the entire planet. And that comparison is the one scientists keep coming back to. Numbers in climate science can become abstract quickly. So, here is a concrete one. Seasonal models from multiple global weather agencies are projecting sea surface temperatures in the central and eastern equatorial Pacific could spike by up to 5.5 degrees Fahrenheit above their long-term average during the peak of this event. 5.5 degrees above normal. In the ocean, to understand what that means, remember that the ocean is not air. It does not heat and cool easily. Warming ocean water by even 1 degree requires an enormous amount of energy. 5.5 degrees above normal in a body of water stretching thousands of miles represents a staggering accumulation of heat energy sitting at the surface of the Pacific and radiating directly into the atmosphere above it. That is the ceiling of current model projections. The floor is more moderate. The uncertainty is real, especially given the spring predictability barrier discussed earlier. But the upper range, if reached, would match or exceed the peak anomalies recorded during the 1997 to 1998 super event, the strongest modern El Niño on record. The National Oceanic and Atmospheric Administration confirmed in May 2026 that the developing pattern carries a 96% probability of continuing through the winter of 2026 to 2027. That winter window is when El Niño events typically reach their peak intensity in the Northern Hemisphere. So the timeline looks like this: emergence through summer, strengthening through fall, peak through winter, lingering effects through spring of 2027. 8 months of an active, potentially extreme El Niño. 8 months of rerouted jet streams, drought, flooding, coral bleaching, fishery collapse, and elevated global temperatures. The volume of subsurface warm water already in the Pacific right now, the heat that has been building for months, is the fuel that determines how high the peak goes. Scientists cannot drain that reservoir before it surfaces. The heat is already there. The question is only how completely it reaches the surface and how efficiently the atmosphere captures it. What scientists can do is model every plausible outcome across that range and identify what each scenario produces. The moderate scenario produces significant disruption across vulnerable regions. The high-end scenario produces something that falls outside the range of most current emergency management planning. Governments were briefed on both scenarios following the May 2026 Watch Declaration. Some responded immediately, others are still assessing. The assessment window is closing, and the frame of reference everyone keeps returning to is the one event in the modern record that showed the world what a super El Niño actually looks like from inside it. The year was 1997. Scientists watching the Pacific in early 1997 saw the same early signals that are visible today. Trade winds weakening, subsurface heat building, sea surface temperatures rising in the central Pacific. By summer of that year, it was clear something large was coming. By fall, the readings were historic. Sea surface temperatures in the eastern Pacific peaked at roughly 4 to 5 degrees Fahrenheit above the long-term average, the highest values ever recorded in the modern instrumental record at that time. The atmosphere responded immediately and globally. The jet stream over North America shifted south and locked in that position through an entire winter season. California received relentless rainfall. Flooding struck coastal communities from San Diego to San Francisco. Cliffs collapsed. Roads washed out. The storms came in waves, one after another, through December, January, February, and March. Meanwhile, Australia baked. Drought gripped the eastern states. Crops failed, wildfires ignited. The Murray-Darling River system, which irrigates a massive portion of Australian agriculture, dropped to critically low levels. In Indonesia, the drought combined with agricultural burning to produce a fire catastrophe. Smoke blanketed Southeast Asia for months. The haze closed schools and airports across Malaysia, Singapore, and Brunei. Scientists estimated the fires released a volume of carbon comparable to a significant fraction of global annual emissions in a single season. In East Africa, flooding killed hundreds and displaced hundreds of thousands of people. In Peru and Ecuador, floods destroyed towns and killed over 600 people. In Brazil, drought hit the northeast. In the western United States, the storms that flooded California left ski resorts buried under record snowfall, while the Pacific Northwest experienced an unusually dry and mild winter. All of this happened simultaneously. Multiple continents, multiple types of disasters, different effects in different places, all connected to one warmer ocean. The global temperature that year spiked to what was then the highest annual average ever recorded. The previous record fell by a significant margin. Scientists described the event as a once-in-a-generation climate anomaly. That generation is now looking at another one. The current subsurface heat in the Pacific matches the readings that preceded the 1997 event. The atmospheric coupling is following the same pattern. The only difference is that the world the current event is hitting runs hotter, carries more moisture in its atmosphere, and has less buffer in its food and water systems than the world of 1997. What happened in 1997 was a preview. What the current signals are pointing toward may not be a repeat of that preview. It may be the full version. To understand what a super El Niño does at full strength, you have to look at the 1997 to 1998 event in detail, because the details are where the reality lives. Indonesia was burning. Forest fires ignited across Borneo and Sumatra in the fall of 1997, driven by a drought so severe that peat soil, normally saturated with water, dried out and began burning underground. Peat fires are almost impossible to extinguish. They burn slowly, deep in the soil, producing dense smoke even when no visible flame is present. These underground fires burned for months. The smoke that rose from Indonesia covered an area larger than the continental United States. Satellite images showed Southeast Asia disappearing under a grey haze that stretched thousands of miles. Aircraft struggled to land. Hikers and outdoor workers in countries hundreds of miles away wore masks daily. Respiratory hospital admissions spiked across the region. At the same time, coral reefs across the Indian Ocean and Pacific were bleaching on a scale never previously recorded. 16% of the world's coral reefs died during the 1997 to 1998 event. Scientists had studied coral for decades and had never seen synchronized global die-offs on this scale before. In the Pacific, fisheries collapsed. The anchovy population off Peru dropped by more than 80%. The fishing industry that those communities depended on essentially shut down for a year. In East Africa, flooding from unusual rainfall killed hundreds of people across Kenya, Somalia, and Ethiopia in a matter of weeks. The same flooding created stagnant water pools across the region, which drove a massive outbreak of Rift Valley fever, a disease spread by mosquitoes that breed in standing water. The outbreak affected both livestock and humans. All of this unfolded over roughly 18 months, one connected chain of events, all tracing back to one anomaly in the Pacific Ocean. The event ended when sea surface temperatures in the Pacific returned to normal in mid-1998. Global temperatures dipped. The jet stream resettled. Australia started receiving rain again. The Pacific fishing grounds slowly recovered. Coral that survived began attempting to repopulate. Recovery took years. Full recovery in some ecosystems has still not been confirmed. Now hold that picture. Indonesia burning, reefs dying across 3 oceans. Fisheries collapsed. Floods killing hundreds across multiple continents simultaneously. That was the 1997 event, happening in a world that was cooler than today's by a measurable margin. The current event is building on a warmer foundation. The subsurface heat is comparable, the atmospheric conditions are similar, and the ecosystems that would absorb the shock are already weaker from years of accumulated stress. The question scientists are working through right now is not whether this event will cause damage. It is whether the systems it hits can withstand the level of damage it is capable of producing. The hottest year ever recorded is a title that keeps changing hands. For most of the 20th century, record annual temperatures were rare events, separated by decades. Then the pace began accelerating. Records fell in the 1990s, then again in the 2000s, then repeatedly through the 2010s. 2016 took the record. 2023 broke it. 2024 broke it again. 2027 may break it by a larger margin than any previous year. Here is the chain of reasoning scientists are following. El Niño events do not just warm the ocean. They pump heat into the atmosphere. This extra heat spreads globally, pushing up average temperatures across land and sea surfaces everywhere. The peak atmospheric warming effect typically arrives several months after the peak ocean warming, meaning that even after El Niño begins to fade, global temperatures continue rising for months. The 1997 to 1998 event caused the biggest annual temperature jump ever recorded at that time. 2023's record high was partly driven by a moderate El Niño that developed that year. The current event, projecting toward a stronger peak than 2023, is expected to push the atmospheric heat signal well beyond what that year produced. Combined with the elevated baseline from ongoing human-caused warming, 2027 is the year when those curves intersect at their highest point. Multiple independent research teams have flagged this. Scientists at research institutions in the United States, Europe, and Japan have each run their models through the coming years and arrived at similar projections. The agreement is not universal. Some models show a less extreme outcome, but the central estimate across the ensemble of models puts 2027 in record territory. A record annual temperature is not just a number. It means the average across every day of that year, across every location on Earth, runs hotter than any previous year. That includes the hottest days of summer in regions already experiencing heat stress. It includes ocean temperatures that are already stressing marine ecosystems. It includes soil temperatures in agricultural regions where crops have specific temperature tolerances above which they fail to pollinate, fail to produce grain, or simply wilt before harvest. A record year does not produce one record-breaking event. It produces thousands of them, distributed across the planet, simultaneously, over 12 months. And then the year after that, the baseline is higher, and the next El Niño, when it arrives in another 2 to 7 years, starts from an even higher platform. The year 2027 is a specific moment in that trajectory. Scientists are watching it approach, not just as a data point, but as a threshold that tells them something important about where this is all going. But before the world reaches 2027, the developing El Niño is about to encounter something that makes its effects on human society painfully concrete. The places where people grow food are already sending distress signals. In the spring of 2022, bread prices in Egypt jumped by 40% in a matter of weeks. The cause traced back to a war in Ukraine and the disruption of wheat exports. But the speed at which prices jumped, and how far they jumped, exposed something fragile about the global food system. It operates with very little slack. El Niño creates a different kind of disruption, but it hits the same fragile system. When multiple major agricultural regions experience stress simultaneously, global food markets respond. Commodity traders track weather forecasts as closely as any farmer. When El Niño watch declarations go out, rice futures move in Asian markets, corn prices shift in Chicago, wheat traders in London adjust their positions based on drought projections for the Black Sea region and the American plains. The mechanism is straightforward. Supply drops, demand stays constant, price rises. When the supply drop happens in one region, other regions absorb the demand. Prices rise moderately. Most people in wealthy countries barely notice. Lower-income countries pay more, but can often manage. When the supply drop happens in multiple regions simultaneously, the absorption capacity disappears. There is nowhere to redirect the demand. Prices spike sharply, and the spike is felt most severely by people and countries with the least ability to absorb it. El Niño events hit rice production in Southeast Asia, maize production in Southern Africa, and wheat conditions across parts of Australia and South America in the same season. These are staple crops. Rice feeds over half the world. Maize is the primary calorie source for hundreds of millions of people in sub-Saharan Africa. When 2 or 3 of these crops underperform globally in the same year, the food security math for the world's poorest billion people changes dramatically. The 2010 to 2011 food price crisis, partly linked to weather disruptions including a La Niña-driven drought in Russia, contributed to political instability across North Africa and the Middle East. Food prices alone did not cause those events, but food stress was a documented contributing factor. In 2026, international agricultural monitoring systems are already flagging elevated risk for food insecurity in the Horn of Africa, the Sahel, parts of South and Southeast Asia, and portions of Central America. These are the regions where food stress from El Niño typically hits hardest, and where the populations are most exposed. Global grain reserves, the emergency buffer that countries and international organizations maintain to absorb shocks, are currently below the thresholds that food security analysts consider adequate for a major disruption. The window to build those reserves is the same window as the weather preparation window. It is closing. And while food systems face stress from above, water systems face a separate and simultaneous pressure from below. Because the same drought conditions that fail crops also empty the reservoirs and rivers that billions of people depend on just to drink. Water is the one resource that has no substitute. Food can be imported, energy can be rerouted, but water must come from somewhere local, a river, a reservoir, a glacier, an aquifer. When El Niño removes the rainfall that feeds those sources, communities face a shortage that cannot be solved by trade. The Nile, the Mekong, the Indus, the Colorado, and dozens of other river systems support hundreds of millions of people downstream. Each of these rivers depends on rainfall or snowmelt in specific upstream regions. When El Niño shifts rainfall away from those regions, river flows drop. Reservoirs behind dams stop filling. Groundwater stops being recharged. In the American West, the Colorado River already operates under severe stress. Decades of overuse, combined with drought conditions that have intensified in recent years, have left Lake Mead and Lake Powell at historic low levels. The Colorado supplies water to over 40 million people across 7 states and northern Mexico. An El Niño-driven winter drought in the Rocky Mountains would reduce the snowmelt that feeds the Colorado and push reservoir levels even lower. In South Asia, the Indus River system feeds Pakistan's agricultural heartland, one of the most densely farmed regions on Earth. The Indus depends heavily on Himalayan snowmelt and monsoon rainfall. El Niño disrupts both. A weakened monsoon reduces summer flow. Reduced snowpack reduces spring and summer melt. A country of over 200 million people faces water stress across its most critical farmland. In the Mekong Basin, which flows through China, Myanmar, Laos, Thailand, Cambodia and Vietnam, El Niño has historically reduced flow during the dry season and altered the flood pulse that fills Cambodia's Tonle Sap Lake, one of the most productive freshwater fisheries in the world. Reduced fish yields from the Tonle Sap affect the nutrition of millions of people for whom freshwater fish is the primary protein source. Scientists use the term water stress to describe regions where demand exceeds reliable supply. Roughly 2 billion people already live under high water stress conditions during normal years. El Niño pushes those regions deeper into stress, while simultaneously creating new stress in regions that were previously considered water secure. The conflict implications are documented across history. Droughts have contributed to political instability, migration and violence in the Sahel, the Middle East and Central Asia. The link is not always direct, but it is consistent. When communities compete for scarce water, and when governments fail to manage that competition, the results extend well beyond agriculture. 2026 is the year that pressure begins building. 2027 is the year it peaks. And running in parallel to the water crisis, in the forests and grasslands that surround many of these stressed water sources, conditions are building for a fire season unlike anything those regions have experienced in the modern era. Fire needs 3 things: fuel, heat, and dryness. El Niño delivers all 3. Drought dries the vegetation, record temperatures stress and kill plants, adding to the dead fuel load. Low humidity pulls moisture out of living vegetation, turning it into fuel as well. Then a spark, a lightning strike, a power line, a campfire, and the conditions do the rest. The wildfire seasons associated with strong El Niño events have set records repeatedly across multiple continents. Australia's Black Summer fires of 2019 to 2020, one of the most destructive fire seasons in that country's history, burned over 46 million acres and killed an estimated 3 billion animals. That event was amplified by an unusual atmospheric pattern called a positive Indian Ocean dipole, but it unfolded during background conditions of long-term drought that El Niño had contributed to in previous cycles. California's worst fire seasons on record cluster around years of El Niño-driven drought disruption. The western United States has seen a dramatic increase in the size and intensity of fires over the past 2 decades, driven by a combination of accumulated drought, rising temperatures, and changing forest composition. El Niño years push those conditions to extremes. In Canada, the 2023 wildfire season burned over 45 million acres, the largest in the country's recorded history. Smoke blanketed major American cities for days, turning skies orange and driving air quality to hazardous levels as far south as Washington and New York. That season also correlated with El Niño warming in the Pacific. The global fire picture under a super El Niño is one of simultaneous fire emergencies on multiple continents, each one demanding resources, firefighting capacity, and public health response at the same time. Aerial firefighting resources are limited globally. When Canada, Australia, Chile, and the western United States all face major fire events in overlapping seasons, there are not enough aircraft or crews to go around. Countries that would normally lend resources to each other find themselves each fighting their own emergencies. Air quality from wildfire smoke now causes documented health impacts hundreds of miles from the fire itself. Fine particles from wildfire smoke penetrate deep into the lungs. Studies consistently link prolonged wildfire smoke exposure to increased rates of heart attack, stroke, asthma attacks, and premature death in exposed populations. An El Niño fire season does not just burn trees, it shortens lives across entire regions through the air that people breathe for weeks and months. And even as fires burn above the surface, something is collapsing far below it, in the cold, dark water where the entire ocean food chain begins. Plankton are microscopic. Most are smaller than the period at the end of this sentence. You cannot see them. You cannot feel them in the water. If you scooped a cup of seawater from the open ocean and held it up to the light, the plankton inside would be invisible to the naked eye. They are also the foundation of almost all life in the ocean. Phytoplankton, the plant-like plankton, produce roughly half of all the oxygen in Earth's atmosphere through photosynthesis. They form the base of the marine food chain. Zooplankton eat the phytoplankton. Small fish eat the zooplankton. Larger fish eat the small fish. Whales, dolphins, tuna, cod, salmon, and the entire global fishing industry rest on that foundation. Phytoplankton need two things to survive: sunlight and nutrients. Sunlight comes from above. Nutrients come from below. In the open ocean, nutrients exist in deep cold water, and they reach the surface only through upwelling, the rising of that cold water toward the surface. When El Niño arrives and warm water spreads across the surface of the Pacific, it creates a stable warm layer that resists mixing with the cold, nutrient-rich water below. The upwelling slows. The nutrients stop arriving at the surface. The phytoplankton, starved of what they need, crash. Satellite instruments that measure the color of the ocean surface can detect phytoplankton concentrations from orbit. Healthy phytoplankton turn the water green. Depleted water turns deep blue. During strong El Niño events, satellite images show vast areas of the tropical Pacific turning from green to blue as the plankton disappear. The blue ocean is sometimes called an ocean desert. Beautiful from space, biologically empty to 1998 event, phytoplankton concentrations across large areas of the equatorial Pacific dropped by over 30%. The effect cascaded immediately through every level of the food chain above them. The animals that depend on this food chain cannot wait for conditions to recover. Fish migrate to colder, nutrient-rich regions at the edges of the affected zone. Seabirds that cannot migrate far enough starve. Marine mammals that depend on fish in specific regions face food shortages that affect reproduction. Female sea lions, for example, cannot produce enough milk for their pups when fish populations collapse nearby. Mass pup die-offs follow within weeks of the plankton crash. In 2026, oceanographic instruments across the equatorial Pacific are already showing the early signs of reduced upwelling and declining surface nutrient concentrations. The plankton decline has not yet reached the scale of a full El Niño event. The warm pool is still expanding, but the direction is clear and the trajectory is consistent with prior events. The blue ocean is spreading, and while the ocean collapses from the bottom of its food chain, the atmosphere above it is absorbing an amount of energy that has its own scale problem. A scale that requires a different kind of comparison entirely to make it real. Numbers in climate science get very large, very fast. Scientists measuring the heat released by the Pacific Ocean during a major El Niño event arrived at a figure that required a different unit to express. The amount of energy transferred from the ocean to the atmosphere during a super event is roughly equivalent to the combined output of millions of large power plants running continuously for the entire duration of the event. Some scientists have described it as equivalent to the energy of millions of atomic bombs, though this comparison is made to convey scale, not explosive force. The energy releases slowly, over months, as heat radiating from ocean water into the air above it. The reason this matters is not the comparison itself. The reason it matters is what that energy does when it enters the atmosphere. The atmosphere is not a passive container. When you add enormous amounts of heat energy to it, it becomes more dynamic, faster, more capable of picking up moisture, more capable of holding that moisture in suspension and then releasing it in extreme bursts. A warmer, more energized atmosphere produces more intense precipitation events, stronger winds, larger storm systems, and more powerful individual weather events than a cooler atmosphere would under the same conditions. This is the physics that links El Niño's ocean warming to extreme weather on land. The ocean releases its stored heat into the air. The air becomes more energetic. That energy finds release in the weather systems that are constantly moving through the atmosphere. Storms get more fuel. Rain events become more intense. Droughts, where the energy goes into drying rather than flooding, become more severe and faster moving. The current event is expected to release a comparable volume of energy to the 1997 to 1998 event, on top of an atmosphere that is already more energized than it was in 1997, because of the accumulated warming since then. Scientists tracking atmospheric energy through a measurement called ocean heat content have confirmed that the current Pacific heat content in the upper layers of the ocean is running at or near record levels for this stage of El Niño development. That heat is going into the atmosphere in the coming months. The storms, droughts, floods and fires that result from that energy transfer are the visible surface of this invisible ocean process. They are not random extreme weather events. They are the release of a specific, measured, trackable store of energy that has been building in the Pacific for months. Knowing the energy is there does not make the events easier to survive, but it does make them predictable enough to prepare for. The preparation window is still open. Barely. And when El Niño finally begins to fade, the story does not end there, because what follows a major El Niño is a cooling pattern called La Niña, and La Niña has its own catalogue of disasters. The recovery from one is often interrupted by the arrival of the other. El Niño does not just fade and leave the world back where it started. When El Niño weakens, the Pacific overcorrects. The trade winds return, often stronger than before. Cold water upwelling surges along the South American coast. Sea surface temperatures in the Central Pacific drop below average, sometimes sharply. This reversal is called La Niña, and it brings its own pattern of global disruption, almost perfectly opposite to what El Niño produced. Where El Niño brought drought to Australia, La Niña floods it. Where El Niño suppressed Atlantic hurricanes, La Niña fuels them. Where El Niño drove drought in the Amazon, La Niña drenches it. The jet stream shifts back, but overshoots its normal position, creating new extremes on the other side. The two events often follow each other in sequence. El Niño peaks in late 2026 or early 2027, then begins fading through spring. By late 2027 or into 2008, La Niña conditions could be developing. For communities that just survived El Niño, this is a brutal reality. A region that fought drought for 18 months suddenly faces flooding. Infrastructure already stressed by one extreme cannot absorb the opposite extreme immediately after. Crops that farmers finally manage to replant after El Niño drought get washed out by La Niña rains. Reservoirs that were empty refill too fast and overflow. The back-to-back sequence of El Niño, followed by La Niña, is well documented in historical records. The 1997 to 1998 El Niño was followed by a strong La Niña in 1998 to 2000. That La Niña brought devastating floods to China, Bangladesh, and parts of Africa, and contributed to severe drought in parts of South America that had just recovered from El Niño flooding. For agricultural regions in Southern Africa, East Africa, and South Asia, the 2-year swing from El Niño drought to La Niña disruption can be the difference between a community that recovers and one that does not. 2 consecutive seasons of crop failure, first from drought, then from flooding, can exhaust the financial reserves, food stocks, and physical infrastructure of even resilient communities. Disaster response organizations track El Niño and La Niña as a paired threat. Preparing for El Niño without considering the La Niña that follows is like bracing for one punch and ignoring the one right behind it. Scientists are already modeling what the La Niña response to this event might look like, based on how previous strong El Niño events set up their successors. The projections are not confirmed. They are early-stage estimates. El Niño and La Niña together form a single cycle. The world is currently entering the warming phase of that cycle under the most extreme baseline conditions ever recorded. And to understand how unusual this moment truly is, you have to step back further than any satellite can reach into the historical record of how this cycle has shaped human civilization itself. Long before weather satellites, before ocean buoys, before thermometers, El Niño was reshaping civilizations. Scientists have reconstructed past El Niño events using physical evidence buried in ice, rock, coral, and lake sediment. Tree rings carry drought signals. Coral skeletons record ocean temperatures year by year. Ice cores in the Andes hold chemical signatures of past rainfall patterns. Sediment layers in highland lakes preserve evidence of ancient floods. Using these natural archives, scientists have traced El Niño cycles back over 10,000 years. The pattern is not random. It pulses roughly every 2 to 7 years, with occasional clusters of strong events and periods of relative calm. What those archives also show is a striking correlation between strong El Niño periods and historical collapses. The collapse of the Tiwanaku civilization in the Andes around 1,000 years ago coincided with a prolonged period of El Niño-driven drought that disrupted the agricultural system that the city depended on. The same climate signal appears in the sediment record of lakes near the site. The weakening of the Tang dynasty in China around 900 years ago correlates with reconstructed records of multi-year droughts linked to Pacific climate variability. European colonizers who arrived in the Americas in the 1600s documented a continent already stressed by climate disruption linked to a powerful El Niño cycle occurring around the time of their arrival. The famines that struck India, China, Brazil, and Africa in the late 1800s, documented in historical records, were directly linked to a series of extreme El Niño events during that period. Researchers estimate these events contributed to the deaths of tens of millions of people through drought, famine, and disease over roughly 2 decades. These were not isolated historical footnotes. They were the largest humanitarian catastrophes of their eras, driven significantly by the same Pacific climate pattern that is building right now. El Niño has always had the power to stress civilizations. What has changed is the scale of the civilization now exposed to it. 8 billion people, global food supply chains tightly integrated and sensitive to disruption, water systems serving megacities built on the assumption of stable rainfall, infrastructure designed around historical climate norms that no longer apply. The cycle is the same. The world it hits is incomparably larger and more tightly connected than any previous version. And the gaps in what scientists can still predict about this event are not small gaps. They are fundamental unknowns that determine the difference between severe disruption and historic catastrophe. Science has come an enormous distance in understanding El Niño. 50 years ago, the concept of a connected Pacific climate system affecting global weather was still being assembled from scattered observations. Today, satellites track ocean temperatures in real time. Buoy networks span the equatorial Pacific. Supercomputers run models that ingest billions of data points and simulate the atmosphere and oceans simultaneously. And still, 3 critical unknowns remain. The first is the exact peak strength of this event. The spring predictability barrier means that current model forecasts carry higher uncertainty than forecasts made in summer or fall. The range of possible outcomes spans from a moderate event to a super event rivaling 1997. That range represents profoundly different real-world outcomes for billions of people. Scientists cannot narrow that range further until the spring barrier passes and the atmosphere locks more clearly onto the ocean signal in late summer. The second is the geographic distribution of the worst impacts. El Niño's general effects on rainfall patterns are well understood at regional scales, but within those regions, where exactly the drought boundary falls, which river system dips below critical thresholds, which coastal area gets hit by simultaneous flooding and sea level rise, these local details cannot be determined months in advance. A community 10 miles from the drought boundary survives. The one inside it may not. That 10-mile difference is beyond current predictive skill at this stage of the event. The third unknown is the most significant. How does this specific El Niño, combined with the current atmospheric baseline elevated by human-caused warming, produce outcomes that exceed what historical analogues suggest? The events that scientists use to model expected impacts, the 1972, the 1982, the 1997 events, all happened in a cooler world, but they are imperfect ones. The atmosphere today holds more moisture, runs warmer, and responds to ocean heating from a different baseline than those past events encountered. Scientists are using historical patterns as a foundation, while acknowledging that the actual outcomes could exceed those patterns in ways that models built on historical data are not fully equipped to capture. These unknowns do not invalidate the warnings, they intensify them. An unknown ceiling on a dangerous event is a reason to prepare more aggressively, not less. The decisions made in the months ahead, by governments, by international organizations, by agricultural planners and emergency managers, will be made inside this window of uncertainty, not after it resolves. And while the forecasting uncertainty is being resolved, the coastlines of every ocean basin are already carrying the weight of everything this event is building. The cities, the infrastructure, and the people closest to the water will feel the event differently than anyone living inland. Half of the world's population lives within 60 miles of a coast. Most of the world's largest cities, Tokyo, Mumbai, Shanghai, New York, Lagos, Buenos Aires, sit at or near sea level. They were built there because oceans enabled trade, fishing, and transportation. The ocean was a resource. It was manageable. El Niño makes the ocean harder to manage. The temporary sea level rise that comes with a strong El Niño event stacks directly on top of permanent sea level rise from long-term warming. Scientists separate these two signals carefully. The permanent rise is slow, measurable in fractions of an inch per year, relentless. The El Niño rise is temporary, but can add several inches to a foot in affected regions within months. Those inches matter on coastlines where storm surge, high tides, and wave action regularly test the limits of flood protection. A seawall designed to protect a city at current sea levels provides less protection when the base sea level has temporarily risen 8 inches. The same storm that would have caused minor flooding under old conditions now causes significant flooding. The same high tide that would have been unremarkable now reaches roads and basements. Miami, Jakarta, Dhaka, Alexandria, and dozens of other coastal cities are already managing increasing tidal flooding during normal conditions. El Niño adds a temporary multiplier to a permanent problem, and in cities that lack robust flood protection infrastructure, the combination is sometimes enough to cross the threshold from manageable flooding to catastrophic flooding. Storm intensity is the other factor. A warmer ocean feeds stronger storms. El Niño suppresses Atlantic hurricanes in terms of total number, but individual storms that do form may intensify more rapidly because of the energy available in the warmer atmosphere. In the Pacific, typhoons strengthening in warmer water are already a documented pattern. The Philippines, Japan, Vietnam, and Bangladesh face the Western Pacific typhoon season from a coastline already stressed by rising seas, while the ocean generating those storms is running at near-record temperatures. Coastal infrastructure in lower-income countries is typically built to lower design standards than infrastructure in wealthier ones. A seawall in the Netherlands is engineered to withstand a 1 in 10,000 year storm. A seawall in Bangladesh may be designed for a 1 in 20 year storm. When El Niño pushes storm intensity beyond historical ranges, those lower design thresholds become dangerous gaps. The people living inside those gaps are the ones with the least ability to evacuate, the least insurance coverage, and the least access to post-disaster recovery resources. The window between the current warning and the peak of this event is the window to reinforce those gaps, not permanently. Permanently takes years, but enough to reduce the worst outcomes during the months ahead. Because beyond the immediate damage of this event, something larger is at stake. The question that climate scientists are watching alongside the current El Niño forecast is not just what this event does, but what it tells us about every event that follows. Every El Niño event has a preparation gap, a window between the first official warning and the peak of conditions, a period when interventions are still possible, when stockpiling food does something, when pre-positioning emergency supplies changes outcomes, when agricultural planners can shift planting dates and crop types to reduce losses. That window exists because El Niño does not arrive overnight. It builds over months. The May 2026 Watch Declaration from the National Oceanic and Atmospheric Administration opened that window. The window will close when conditions peak, likely in the winter of 2026 to 2027. By that point, drought is entrenched, flood damage is underway, fisheries are already collapsed, and the ability to change outcomes has largely passed. What happens inside the window determines how many people suffer and by how much. The most effective interventions are early and specific. Governments in vulnerable regions that pre-position emergency food supplies save lives during the peak shortage months. Agricultural extension services that advise farmers to shift toward drought-resistant crop varieties before the planting season see smaller yield losses. Water utilities that begin conservation measures before reservoirs drop below critical thresholds avoid emergency rationing later. Coastal authorities that issue early flood advisories before storm season give communities time to elevate belongings and reinforce structures. These are boring interventions. They do not make dramatic news. They happen in agency offices and spreadsheets and agricultural advisory bulletins. They are harder to photograph than a flood, harder to broadcast than a wildfire. But the evidence from previous events is consistent. Early action in response to El Niño forecasts measurably reduces damage compared to regions that wait. The 1997 to 1998 event generated enormous damage, but countries and regions that had used the warning period to prepare fared substantially better than those that did not. Southern Africa's response to that event, where some governments pre-positioned food aid based on forecast drought, is studied as an example of how forecast-based action works when the political will exists to fund it. 2026 has better forecasts than 1997. Better satellite data, better buoy networks, better model accuracy. The warning is clearer now than it has ever been for any previous El Niño event. The question is whether the decision-making systems that receive that warning are fast enough, well-funded enough, and politically capable enough to use the window. Some governments have already begun responding. International aid organizations have begun mobilizing pre-positioned supplies in the highest-risk regions. Agricultural advisories have gone out to farming communities in parts of East Africa and South Asia. Others are still assessing, still waiting for more certainty before committing resources. The certainty that more waiting will produce is limited. The spring barrier is real. The uncertainty will not fully resolve until summer, and summer is later than optimal for many of the decisions that matter. Every week inside this window is a week that could be used, and the world that exists after this window closes will be shaped by the choices made inside it. When this El Niño ends, the world will not return to where it was before it started. That statement is true of every major El Niño event. Coral that dies does not grow back in years. Fisheries that collapse need years to recover, if they recover fully at all. Agricultural regions that lose topsoil to El Niño flooding take years to rebuild soil fertility. Glaciers that melt during the heat spike do not reform. Forests that burn do not return as old growth for generations. Each major event leaves the world slightly more depleted than it found it, and then the climate baseline rises a little further. And then another El Niño arrives. The cycle is natural. The escalation is not. The escalation is the product of a warming planet, lowering the threshold at which natural events cause irreversible damage. Scientists tracking this trajectory describe a concept called climate shifting baselines. Each decade, the starting point for what is normal moves slightly higher in temperature, slightly more stressed in ecosystem health, slightly more strained in food and water security. Events that were once extreme become frequent. Events that were once catastrophic become survivable only if preparation improves fast enough to keep pace. 2027 will be remembered as a year of records. What comes after it depends on decisions being made right now and the decisions that will be made in every year that follows. The El Niño building in the Pacific right now is a natural event. It has happened before. It will happen again. The fishermen who named it in the 1600s were watching the same ocean, the same warming, the same disappearing fish. They passed the warning down through generations because they understood that knowledge was the only defense available to them. Today, the knowledge is deeper. The warning systems are better. The forecasting is more precise than anything those fishermen could have imagined. Satellites track the heat pulse from orbit. Supercomputers project its trajectory months into the future. Scientists issue official watches with probability figures down to single percentage points. The gap between what we know and what we do with that knowledge is the most important variable in how this ends. Every major El Niño in the historical record caused damage that was partly unavoidable and partly the result of decisions made in the warning window before it peaked. The unavoidable part is already set. The Pacific heat is there. The subsurface pulse is rising. The trade winds have eased. The part that is still being decided is everything else. The world that comes after this event will be shaped by how the world responds to it, before it peaks, during its height, and in the years of recovery that follow. Every reef that survives because water temperature stayed just below the bleaching threshold due to reduced emissions matters. Every farm that stays productive because drought-resistant crops were planted in time matters. Every coastal community that avoids the worst flooding because early warnings arrived and were acted on matters. The fishermen named the thing. The scientists mapped it. The satellites track it. Now comes the part that is up to everyone else.